All right. We're now going to start talking about a new part of calculus here for us. Um, and this is quite an interesting facet of calculus, but in order to get there, we really need to lay some foundation. And that's going to start with something called sequences. Right? You've actually dealt with sequences before when you did Riemann sums, right? You added up a sequence of areas of rectangles, right? Here we're going to look at this a bit more generally, right? So an example of a sequence, or I guess let me say a definition of a sequence is really just a list of numbers, right? With some order. So for example, 1, 2, 4, 8, 16, 32, 64, and so on, right? This is an example of a sequence. Now, a sequence, may or may not have an actual pattern to it. This one, you can probably see, does have a pattern. But, there's no reason we have to have a pattern. We could have a sequence of random numbers, for example. Right? So, in order to work with this mathematically, we need to have some kind of a notation for sequences. So, often in a sequence, we'll have we'll list out terms like this: A1, A2, A3, A4, so on. Right? This is one way we can write down an arbitrary sequence. If we compare these two, this would be the A1 term, this would be the A2 term, A3, A4, A5, so on. Right? Now, sometimes you start sequences at n equals 1, sometimes you start them at 0. Those are the common two. There's no reason you couldn't start with, say, A4, right? But it's pretty common to start with 0 or 1, right? So this is one way to write down an arbitrary sequence. Some other notations you might see are things like AN, where n goes from 1 to infinity. This is something you might see. Another one, and this is actually probably the most common one you'll see, is just AN inside of some brackets. All right, so normally when we write down a sequence, we do write it down just a list of numbers inside brackets like this, or just a general term here. All right, so these are all for an arbitrary sequence. All right, I'll just say these are notations. All right, so as you may or may not remember from doing Riemann sums, this number, the subscript here, this is called the index. So we say like this is the first term of the sequence, this is the second term, this is the third term, and so on. Right? So yeah, so let's again compare. Let's say for this example sequence up here, let's go ahead and compare that to the example. So compared to the example, A1 would be 1, A2 would be 2, A3 would be 4, A4 would be 8, and so on. Right? So obviously, just having a list of numbers like this isn't necessarily the best way to work with a sequence mathematically. We'd like some kind of formula to go along with that. Right? And this is where something called an implicit or an explicit formula comes into play. So let's look at the sequence here. Let me again, let's write it down like this. Let's just write down the terms of that sequence. Oops, not 6. It's 8, 16. All right. One way we can write down a sequence is using the implicit formula. So what does that mean? Well, in order to get the implicit formula, we want to look for a pattern in here. We want to look for if I take the previous term, how do I get the next term from that? Right? This is a first order recurrence relation. We could get something more complicated, but this is a first order one. So what are we doing here? From here to here, we multiply by 2. Here to here, we multiply by 2. Right? Each time it's multiplied by 2. So how do we write this down mathematically? Well, what we do is we say, well, if I have the previous term an, right, let's say that's the term I'm at right now. If I want the next term, an plus 1, what I gotta do is take the one I'm at right now and multiply it by 2. Right? This right here, this is called a recurrence relation. Right? It's also called an implicit formula. Right? Now, the implicit formula here, it does require you to specify some information here. For example, we need to say, the formula applies for, here n equals 1, 2, 3, and so on. All right. Another thing we have to specify is we need to specify what the first term is, right? Because we can't plug n equals 0 into this. There's no way we can do that. So we need to specify that our first term is 1. So when we're writing something down with an implicit formula, really the way we want to do this is say, all right, well, an plus 1, actually, it's probably better to start this way. Let's say, all right, our first term, a1 is equal to 1. And then from there onward, oops, I don't know why I wrote a comma there. Moving onward from there, we can use this recurrence relation. So this would be sort of how we should write down a recurrence relation for our sequence. Right? So the nice thing about a recurrence relation is it's really simple to get your hands on. All right, you just look for the pattern in your functions here. So we just say, all right, we're multiplying by 2, by 2, by 2, by 2. We keep multiplying by 2. So that tells us our rule. How do we move from one to the next? Right? Now, the problem with recurrence relations like this is, in order to get a term far along in the sequence, I have to know the one that came before it. To get that one, I have to know the one that came before it. So my question is, how do we compute A20? Right? How do we do this? How do we actually get our hands on this term? Let me make that 0 a bit bigger there. How do we actually compute that? So in order to compute this, right, with the recurrence relation, to get A20, we would need to know A19. To get A19, we'd have to know A18. To get A18, we'd have to know A17. And you can see that's not fantastic, right? That's a lot of work. Well, there's another way we can write down a sequence. Instead of using a recurrence relation or an implicit formula, we can try and write down an explicit formula. Right? So let's think about that. So we know A1 is equal to 1. We know A2, let me do this. Let me put the n value up top, the an value here. Right? So here, n equals 1, 2, 3, 4. Let's say we do the first 5. Right? And we know the values in this sequence are 1, 2, 4, 8, 16. Okay? So how do we do this? Right? So to get from here to here, I multiplied by 2. So let me say, this is maybe 1 times 2 to the first power. Right? To get from here to here, I multiplied by 2. Now what I'm going to do here is, instead of simplifying this, I'm going to keep building on this. So actually, maybe I don't even want that 1 there yet. So I'm going to build on this, the simpler version. Right? So to get from here to here, I multiply by 2. So now it's going to look like this. Right? To go from here to here, I multiplied by another 2. And to go from here to here, I multiplied by another 2. Right? So writing out your function, your sequence like this, saying how we move from one term to the next, and not simplifying it, can really help you build what's called an explicit formula. Right? So if we look at this, there's a certain pattern we can try and tease out here. Right? So if we look at this, here, this is just 2 to the 4th. This is 2 cubed. This is 2 squared. And I had it earlier and erased it, but this is 2 to the first power. And if you think about it here, this is 2 to the 0 power, right? So if we look at how this is progressing, and let's just, move one more term. Is this really 2 to the 5th power? Right? Well, the 6th term, if we go back up here, was 32, which is indeed 2 to the 5th power. Right? So what we can say is an explicit formula for the sequence. This would simply be given by an is 2 to the n minus 1, because each term here is always 2 to the power 1 less than the index. And this applies for n equals 1, 2, 3, and so on. Now look at the beautiful thing here with an explicit formula. All right? The beautiful thing about an explicit formula is, if I want, say, the 20th term, all I have to do is just plug in n equals 20. So the answer to that question earlier, A20, well, that's 2 to the 20 minus 1, which is 2 to the 19, which is 524,288, if you were interested. Right? So this is something you could toss into Mathematica to double check. All right? So the explicit formula is, generally speaking, a lot easier to work with. Right? Now, it's not necessarily always the best. There are situations in which recurrence relations are wonderful. The best thing about a recurrence relation is it's really easy to program, right? And really easy to compute. Whereas an explicit formula, it's really easy to work with mathematically, but it might be slightly more computationally intensive. Right? And again, it really depends on what you're doing, what your operations are. Again, the best thing about an explicit formula is you can pick out the value of any point in the sequence at any time. Right? So one more thing I want to say in this video here is, you can, if you know your implicit formula, you can always use that to double check your explicit formula. So here we knew that an plus 1 was 2an. Right? We can always verify that, our two formula agree by plugging in the explicit formula into the implicit. So an plus 1 would be 2 to the n plus 1 minus 1. And that should equal 2 times 2 to the n minus 1. Right? We're just plugging in the explicit formula here? Well, simplify the exponent here, we get 2 to the n. Combine these exponents, we get 2 to the n. And then, well, those two match up. All right? So, hopefully that makes sense, and see you in the next video.